Well, we've heard a lot today about developing models that really try and look at how or predict how an ecosystem might respond to a change in one or more environmental variables. We've also heard that to do some of these models that connect biological and physical ecosystems, that we need to be very careful about the time scales, the space scales, and even the parameter scales in order to link these models, but also to link models to monitoring. And what I'm going to do today is to focus in at one of those response units, and that's a fish. And in an effort to try to get better insight in some of the time, space, and parameter scale issues when linking models. So for the next 15 minutes, make believe you're a fish, and look and think about what sort of what you might think might be good habitat quality. And fish habitat quality is something that is a commonly used term, but it's also very explicitly defined by NOAA as essential fish habitat, which is really affects the survival, reproductive success, growth, and reproduction of a fish. In a coral reef or possibly even a river system that has logs, a habitat structure is normally considered a component of fish habitat quality. But to think about it more broadly, let's think about what might be good habitat quality for a pelagic fish. How do we define it? How do we measure it? How do we compare it among species or ecosystems across the physical and biological gradients, across time and space, and in response to changes in environmental variables? I'm going to define habitat quality specifically as a measure of the growth rate potential of a fish. Growth rate potential is simply defined as if I put a fish in a body of water and it has known characteristics of, let's say, food and temperature and so forth, how quickly would that fish grow? It's a measure of habitat quality from the perspective of that fish. Now, why do I think growth? Why do I use growth rate? Well, growth rate clearly is an integrative response of how a fish might perform in an environment. It relates directly to its reproductive capability and even its survival. And it's based on combining the fish's physiological requirements to the prevailing environmental conditions. It's going to differ among species and life stages. It's going to vary in time and space, and it's going to be a nonlinear response. We heard it by Steve before me that phytoplankton might be one of the biological components on the right-hand side of the equation that's fairly well understood. I'm going to argue that we really can model fish growth rate fairly precisely. It's done by a mass balance equation. If you know the physiology of the fish, you can model its growth rate fairly well. It's fairly well developed and applied in a lot of areas. If we take a volume of water about the size of this room and it's uniform under known conditions, we can put a particular species in there that has known physiology and pretty much predict how well that fish would grow if placed in that particular environment. But growth rate of fish is a nonlinear process. What's shown here is if you give a striped bass a unlimited food supply and put them in different temperature and oxygen conditions, they will have a nonlinear response to that growth. What that means is there are certain areas where with unlimited food supply, they will still lose weight. And it's both nonlinear with respect to temperature, oxygen, and the interaction of those. And that's true of many species that have been looked at. Another way to look at nonlinearity in this case is that you cannot average the environmental conditions in order to get a measure of average growth, because the growth rate at 18 degrees, for example, in this case, and the growth rate at 22 degrees is not the same as the growth rate at the average temperature. That says, at least in case of fish, that averaging temperatures over a 1 degree centigrade, beyond a 1 degree centigrade, can lead to errors in estimation. Another thing, if you average across spatial averaging, what tends to happen is you lose the very high values and you lose the very low values. And it may be those very good elements of the habitat or very poor elements of the habitat are really driving the overall response. So what that means is you need to divide the habitat into very small spatial scales that are uniform in environmental conditions, and I won't go into this. This is one of the models we do, but all of the rest of the figures I'll show will be done using this process where we develop a measure, we calculate what the growth rate potential of that particular fish is in very small volumes of water, and then combine that over very large areas. And I'm going to look particularly at how hypoxia affects fish habitat quality, and I'm going to be focusing on the Chesapeake Bay and the Gulf of Mexico. The fish I'm looking at are striped bass. Striped bass is the same species that's found in the delta here. Bluefish, and then two of their major prey, a bay anchovy and menhaden. Let's look in a very simple case now of just the striped bass. Let's take one point in space in the Chesapeake Bay, and using monitoring data, just monitoring data for temperature across an annual cycle and dissolved oxygen across the annual cycle. And then the bottom figure shows the growth rate potential, or basically habitat quality for striped bass in those conditions. You can see it varies across the year. It varies with depth. Red areas are always areas of good growth. And it's driven by, in this case, temperature and oxygen, and we assume that food is unlimited. Now, if you look at that over different years, you see quite a bit of variability over the years. And just driven by temperature and oxygen alone at that one location, you get a high degree of variability in what the annual scope for growth would be for that particular species. You can look at the same thing in a number of different geographic areas and in the same year and get quite a bit of difference in variability. Again, this is a measurement of what that habitat quality would look like for that particular species. You can put it together in a three-dimensional look at the entire entire Chesapeake Bay. And one of the ways to just simply summarize that is look at a frequency histogram of habitat quality in any particular year. And what this means is that if you look at the, if you look at the frequency distribution and growth rate potential, here's the zero value, and that in the summertime, most of the area in the Chesapeake is negative growth, meaning they'll lose weight, but there are still areas where they have positive growth. That's a very simple way to characterize what that entire Chesapeake Bay would look like for the striped bass in terms of its habitat quality. I'm going to switch now to another species as another example. This is the bay anchovy. The bay anchovy is probably most similar to the delta smelt here in the sense that it's one of the most, well, I guess maybe not so similar. In the Chesapeake, it is one of the most common species of fish, probably the most numerous species of fish, but it's similar to the delta smelt in that it's an annual species. It lives to be 1 year. And you can take monitoring data of, in this case, temperature, dissolved oxygen, and zooplankton, and get functional relationships and define, in essence, in this case, a two-dimensional view, or actually it's a three-dimensional view of the what that habitat quality looks like for the bay anchovy. If you put this together for a number of different years and look at how that habitat quality varies, and this again is for, I believe it's summarized for the summer, you can see that over the course of the years there's been a large decline. In this case, blue is high and red is low. If you look at the growth rate potential, and again for that whole year, relative to other measures of abundance of that species, this is based on seining and random trawling, you can see that that annual scope for growth is a really good indicator of the change in that population level. This would be expected probably in a species that is an annual species. If you're looking at how well it grows over the course of that year, that really defines a lot about its health and correlates well with the abundance. Okay, I'm going to look at another species now, again the Chesapeake Bay. This is the Atlantic menhaden. And I'm going to be looking particularly at the Patuxent River, one river system that's pointed out here in the Chesapeake Bay. The menhaden is an interesting fish in that it feeds primarily on phytoplankton. So what we did is connected the growth of menhaden to really a watershed model that was connected to a 2D water quality model that produced phytoplankton. And we did that under and this is probably too much information, but we did it under, let's say, looking at 3 different times of the year in June, July, and September, but under conditions where, in terms of the watershed, we doubled the urban use of the land, had a baseline condition, and halved the urban use of the land. That affected both runoff, water flow, nutrient loading, as well as, of course, consequences to that, which is phytoplankton, and ultimately growth. And we can then look at how those changes in watershed use changed the growth of particularly this particular species, was the Atlantic menhaden. I can summarize it. We found some very interesting things. One of them is that the center line here is the medium use, and we had the highest growth of menhaden that we saw in any of the other times. And it's really a complex interaction of the fact that where the phytoplankton grows, it's changing of the flow rates and residence time that allowed that phytoplankton to grow particularly well in that shallow area that produced Atlantic menhaden. We're also able to connect that menhaden growth model to a 3D water quality model. In this case, this is a 3D Corps of Engineers water quality model of the Chesapeake Bay that produces temperature, dissolved oxygen, and chlorophyll in particular, around 4,000 cells, and we narrowed it down to a daily output of that. And we can develop then the growth rate potential for the Atlantic menhaden across the year, and if we sum it up, we can get a carrying capacity for that species. So what I've sort of shown is that there are ways to begin to connect these models. All of the models I've shown where we're connecting the water quality model to the fish model have not been an integrated model. It's been taking output from one and putting into the fish model. It was really difficult to put the fish model into the hydrodynamic model because they just weren't capable of doing that. Now they've since gotten a situation where menhaden is now part of the 3D water quality model, and there's a feedback loop, and that the menhaden can eat the phytoplankton and reduce the amount of phytoplankton and change its production dynamics. So I'm going to move to the Gulf of Mexico to give you some other kinds of examples. And again, we all know Gulf of Mexico has a dead zone, and where the oxygen goes to zero, and we've been studying it by adding the food element to the species we're talking about. We're going to move now to the predators, but we're actually going to measure what the food is available in the field. We're using underwater acoustic techniques and some other techniques to give us continuous maps of what's beneath the boat, and what it looks like is a figure something like this, where we can get curtains, in this case is of dissolved oxygen level, across the shelf. And this shows just the overall number of fish, prey species per square meter surface area. But if I go back and looking at growth rate potential, what we have here is a cross-section of temperature versus oxygen, temperature versus distance, showing the oxygen concentration, the temperature concentration, and in this case the prey density, how much food is out there. And this is a map of what that combined habitat looks like to the bluefish in this case. This is areas in red are areas where they would grow well. You can see there's a lot of areas. It's nonlinear. It's a combination of all three of those factors. If I look at that same thing for the striped bass, this is what they see. And the reason for that is because the temperatures are too warm for the striped bass. If I showed you one for the Chesapeake Bay, where both of these species also coexist, the maps would look identical for the striped bass and for the striped bass and the bluefish, because the temperatures are such that they can both do well under those conditions. If I found a colder area, then the striped bass would be doing better. So that's a temperature-driven change, but you can have the same environmental conditions that are going to look quite different for the two species. I'm going to switch over and talk a little bit about time dimensions, time scales, and I've heard Steve gave a nice presentation about talking about frontal systems. One can think where you have a sharp gradient in space, but you also can have sharp gradients in time as well. We were, I want to say, lucky enough to be out during a tropical storm in the Gulf, and just before and just after the tropical storm. And the top figure shows the physical chemical structure on the left and the structure of where the fish were distributed in the water column on the right before the storm, and then after the storm, everything was mixed up. The food got really mixed up as well. And one question would be is, do these kinds of storms really change the system in such a way that there might be a pulse of food or a pulse of lack of food? In our case, it looked like it was a pulse of positive growth. And how do these events in the system really impact what's going on? We don't really know. It's very hard to monitor events, and it's very seldom taken into account in terms of modeling. If we look at it on the complete other end of the time spectrum, let's look at climate change. And what we did is we modeled what the climate change impact would be on Chinook salmon, the same salmon in the Delta here, but we looked at it in the Great Lakes, and modeled it for under base conditions at the year 2030 and the year 2090. And what these figures show is the sort of the annual, the x-axis or the y-axis is depth, and the x is time across year. And you can see that there is one would expect, since Chinook salmon is a cold water or cool water animal, that warmer water temperatures would somehow not be good under climate warming. And what happens is that area here under 2030, it gets too warm for the salmon to grow, and even much warmer, so there's areas that become weight loss areas. But it turns out that because they have a warming begins earlier in the year and runs later in the year, you actually get an annual growth cycle that is far better under climate warming than it is under base conditions. And what this points out is that time duration is also a factor we need to consider. How long, in terms of climate warming, it's not just how warm it gets, it might be when initial conditions start getting warm and how long they stay warm, and that annual cycle would really be important for fish. So what I've been talking about so far has largely been a measurement of the habitat as viewed from the perspective of an individual fish or type of fish. I haven't said anything about where that fish is or how that fish exploits that habitat or whether or not it exploits that habitat. So the question is, how effective is a species at really exploiting the prevailing habitat conditions? In order to do that, we need to know how the fish sense that habitat, what their movement patterns are, and how they exploit it. And a simple way to look at this, if we look at the percent of the water volume and look at the top bar graph, which is what we would measure, how that habitat is distributed, what's the available habitat? Well, the fish could be really smart, and they could go and find those areas of high growth and exploit those areas of high growth. They could use temperature preference, they could use some other way to do that. On the other hand, the fish may be very ineffective at using that habitat. So just measuring the habitat out there without knowing how fish are moving and where they're moving and what their time scale of movement is does not get to the answer of actually forecasting what growth is. We can measure how the habitat changes, but you need to take, as Steve mentioned earlier, the animal behavior into account to really look at the consequences. I'll just illustrate that in one simple way. In the Gulf of Mexico, one of the things we wanted to look at is how were fish even in the area where there was hypoxic or almost a dead zone conditions. We would see them if we'd go along acoustically. We would sometimes see fish or something down there that looked like it shouldn't have been there because of oxygen conditions. So this is a high-frequency DIDSON that gives you, in essence, a video. And what you're looking at here is the bottom 5 meters of the water column. And down here we're about 1.5 milligrams per liter, very low oxygen concentration for fish. And you can see some fish going along in here. This is the stationary. Now you see a group of fish that are actually in hypoxic water and then swim out. And this gives us, again, that time scale of a transient coming in and using habitat that is largely would be characterized as uninhabitable. So with that, I'm just going to summarize some take-home messages. One is that a lot of the behavioral and physiological reactions of fish to their environment are nonlinear. And that means you need to be really careful in terms of making any sort of correlations of environmental factors with response of fishes. They're multiple and interactive. I've showed you a little bit about the prey availability, temperature, and oxygen, but they are interactive things that are occurring. The time, space, and parameter scales of biological models often differ quite a lot from the time, space, and parameter scale models of those trying to move water and predict where water's going. Spatial scale and time scales, averaging across those can lead to some difficulties. I said the time duration is important. The physiological and perceptive capabilities are really important, and they are going to differ among species and among life stages within a species. And then finally, the habitat quality, it should be, does not necessarily equal habitat use. So with that, thank you.